And now, he's no dud. He's going ballistic right here on our stage. The canonical physicist, that big shot, our moving local frame of reference, Professor Clint Sprott.
Welcome to the Wonders of Physics. Now, I'm sure you wonder why I rode in on this contraption. Well, it's to illustrate a principle of the physics of motion. We're going to be talking about the major areas of classical physics today on the sign on the wall. And the thing I was trying to illustrate was that if you projected an object vertically upward from a moving car, the object will stay always above the car. And I can illustrate that with a smaller example of the same thing here, where we have a small car that has a spring and a ball inside. And I can give it a push, and the ball goes up and comes down right where it started in the car. So this is an important principle of physics that has to do with Newton's laws, named after Isaac Newton, a famous physicist who lived many years ago and developed the laws that even today we use to explain the way in which things move. Now, for the next example of the physics of motion, I need a volunteer. Who will help? All right, come down here. Turn around. Tell us your name.
Casey.
Casey. Okay, Casey, are you good at sports?
Somewhat.
What do you play?
Baseball.
Baseball. Are you good at it?
Pretty good.
Did you ever go bowling?
Yeah.
You good at that? What's the highest you've ever bowled, Casey?
100.
100. Well, that's pretty good. Okay, Casey, would you turn to your right and go over to my assistant, Mr. Lovell? We're going to take Casey bowling using an 18-pound bowling ball suspended from a wire from the ceiling to make what we call a pendulum. Now, a pendulum is any mass on the end of a string or a wire suspended so it can swing back and forth. You feeling strong, Casey? Just pretend it's like a baseball. Hold it up against your nose. Put your head against the wall. When I say, I want you to let go. You ready? Yeah. Let go. Put your hands down by your side, and don't move. Once more. Thank you, Casey. Now, the reason we could do that safely is a very important principle of physics that we call the conservation of energy. When the ball was up at his face, it had potential energy because it was higher than it was when it was down here. That energy was converted into the energy of motion, so-called kinetic energy, when he released it, and then eventually back to potential energy when it swung back in front of his face. And because of this law of the conservation of energy, we could be pretty confident that it would come back just about exactly to where it was released and no more. Well, there are many examples of the way things move, and here's another thing. Any of you have one of these at home? What does it look like? That's right, a bicycle wheel, and that's exactly what it is. What do you have in your bicycle wheel? What is inside the tire? Air, that's right. You know what's in our bicycle wheel? Concrete. That's right. And that makes it quite heavy. And it also means that when I spin it around, it's kind of hard to stop it. It's got a lot of what we call angular momentum when it spins around like that. But what I'm going to do is suspend this from the wire, as we did the bowling ball, and make it kind of a curious pendulum out of it. Now, instead of swinging it back and forth as we did before, what I'm going to ask is Mr. Lovell to give it a spin here. And we will make what is called a gyroscope. And you notice it goes round and round. The wheel is going around, but also it's going around in a different way. And not only that, but it seems to be defying gravity. It's standing out here and it's not falling. Now, when you ride your bicycle, have you ever noticed that it's easier to ride the bicycle when you're going fast than when you're going slow? You notice that? You ever wondered why that is? Well, in part, the reason has to do with the angular momentum of the wheel of your bicycle. When something's spinning like that, it's really kind of hard to tip it over. But when I stop it, like this, then it tips very easily. And so this is that principle of the conservation of angular momentum that tends to keep the wheel upright, spinning in whatever direction it's going. And the faster you're riding your bicycle, the faster the wheel is spinning, and the more upright it tries to stay. So that's kind of neat. Let me show you another example that has to do with the law of motion. I have here a bucket. You know what's in the bucket? That's right, ordinary water. What do you think would happen if I turned this bucket upside down over my head? I'd get wet. You think so? You're sure now? If I spin it fast, maybe I won't get wet. Let's try it. Well, that's right. If I spin it fast enough, I don't get wet, and that's because of a principle of physics that we call inertia. Inertia is the tendency of objects at rest to remain at rest, or objects that are moving to continue moving in the same direction. And when the water is way up over my head, it's moving that way. It's not moving down, it's moving horizontally. And it tends to keep moving that way. And it's only by pulling on the handle of the bucket that I can make it fall. And so if I spin the bucket around rapidly enough, it doesn't fall. Now here's another example that involves a peculiar kind of motion. Any of you have a yo-yo? That's right. This kind of looks like a big yo-yo, doesn't it? Well, I'm not going to use it like a yo-yo. I'm going to use it in a slightly different way. I'm going to put it on the table here, and it's got a string wrapped around it. And I'm going to pull on the string. Now I want you to tell me whether you think when I pull on the string, the yo-yo is going to roll toward me or away from me. Who thinks it's going to roll toward me? Who thinks it's going to roll away from me? Most people think it'll go away. You know, that's fine in science. It's okay to have different opinions, and it's okay to voice your opinion. And it's also okay to be wrong. But you know, scientists don't just vote on things, and we don't just argue about them, but we go into the laboratory and we do an experiment. So that's what we're going to do now. I'm going to pull on the string, and most of you thought it would go away from me, right? Let's see. It comes toward me. So many of you were wrong. But watch more carefully. Let me pull again. I can make it go away. I can make it come toward me. I can make it go away. Either direction, I can make it go. Now that's very strange, isn't it? It almost looks like magic. And in fact, you know, there's a lot of physics in magic. And if you're interested in magic, studying physics is a good way to start, because a lot of the things magicians do make use of principles of physics. Well, you know, another way in which things move is when something falls. That's a familiar example of the physics of motion. And I have a couple of objects here, and I'm going to drop them. And so you can see it a little better. I'm just going to hop right up on the lecture table. Now in this hand, I have what? That's right, it's a rubber ball. What's in this hand? That's right, it's a wad of cotton. Now I'm going to drop the two side by side, and I want you to tell me whether you think the ball will hit the ground first or the wad of cotton. Who thinks the ball? Who thinks the wad of cotton? A few people. Who thinks it will hit at exactly the same time? A lot of people think that. Again, it's fine to have opinions, but let's try it. I'll drop them together. I hope you can see the ball hit the ground quite a bit before the wad of cotton. Now there's a reason for that, and the reason is not because the ball is heavier, but it's because the resistance of the air affected the cotton more than it did the ball, and it slowed the cotton down. And we can actually illustrate that with a little apparatus right here. I have a long glass tube, and inside of this are a couple of objects. Can you see what's in here? What do you see? A ball of cotton and a penny. Anything else? In fact, there's air because this valve is open and the air has come in. Now I want to repeat this demonstration by starting with these at one end and just flip it upside down and see how fast they fall. Well, maybe it's hard to see the penny from the back, but I hope you can hear it. And you can see that the penny falls much faster than the cotton. And that's perhaps not too surprising. It's just like what we did here. But the reason I did this in a tube like this is so that we can take the air out of the tube. And in order to do that, we use a vacuum pump. Now, a vacuum pump is a little like your vacuum cleaner at home, except it makes a much more powerful vacuum. We can take all of the air out by putting this hose on it, connecting it to the vacuum pump, and turning it on. And you see a gauge here, and it's coming down towards 0. And when it gets down to 0, all of the air has been removed from the tube. So what I'm going to do now is close this valve. And once that valve is closed, we don't need the vacuum pump, so I'll turn that off. In fact, I can let air into the vacuum pump. You see the air coming in here. And then I can disconnect the hose. And I have this tube with what in it? A penny? Ball of cotton? Anything else? A little bit of air, that's right. You know what we call that? A vacuum, that's right. It's not a perfect vacuum, it's a partial vacuum, but it's pretty good. So I'm going to start with these at one end, and I'm going to flip it over as I did before. Once more. And one more time. And you see they fall right side by side. So if we can remove the air resistance, in fact, it is correct that objects fall at the same rate, they hit the ground at the same time if they're released together, no matter what their mass or what they're made out of, how heavy they are, or anything. Now to show you there are no tricks, I'm going to let a little bit of air in. See the air going in? And then we'll do it one last time. And again, the cotton moves very slowly. Okay. Well, now what?
Yeah, let me in here.
Oh my goodness, it's Albert Einstein.
Yeah. Oi, Gesundheit.
Have you ever seen one of those?
I don't think, not for a long time, Professor Sprott.
Well, you came at the wrong time. Have you ever been to Yellowstone Park, Dr. Einstein?
No, I never have made it there.
You've never been there. You know they have things in Yellowstone Park that erupt and shoot water up? You know about that?
Well, of course I know about the geyser principle. You know, I came in right when you finished that tube demonstration because I'd just been talking with my friend, Monsieur Galileo Galilei. Yeah, and Mr. Galileo Galilei, he told me, you know, that he was really the first one to do this experiment. He said that, you know, way back then, people thought that the heavier objects would fall faster and the lighter objects would fall slower. Now, people think he climbed up the Tower of Pisa with these balls and he dropped them over the edge, but let me tell you, my friend Galileo, he is not that energetic. He really just rolled the balls down the inclined plane, and he could see from that the same acceleration applied to different masses of objects. So what he did was groundbreaking at the time. He took this simple idea, and he thought hard about it, and he did the experiment and changed the world. Well, this is something that happens all the time in science. Really big breakthroughs occur when people think very hard about very simple things. And so, you know, I brought a demonstration with me to show you this, okay? Does anybody know what this thing is called? Someone down here said a tornado. It's, well, maybe a tornado in a bottle. I would not bring a whole tornado into this room, right? But if I turn it upside down, you notice that the air goes glug, glug, glug up, and the water goes plop, plop, plop down. But it is very slow. But watch what happens when I give it a spin. When I give it a spin, we see a tornado develop. You can see the nice tornado shape. Now, something that you cannot see in the back row is on the sides of this tornado, there are some lines that spin on their way up, and there are some lines that spin on the way down. Now, these lines, they're called the counter-propagating vortices. And you know, this is something that even though this is a children's toy, that the scientists, we do not understand very well. So here's something very simple that maybe one of you young scientists can think very hard about and come up with an explanation. Well, this is all I want to share with you. Think very hard about very simple things, and you are well on your way to becoming a very good scientist. Thank you.
Well, such a surprise to have a visit from someone so distinguished. But you know, Albert Einstein is a person who thought very, very deeply about some very simple things, like space and time themselves. And he came up with some very important theories about the way things work when they move very, very fast. Oh, an umbrella on the front row. Very handy. Okay, so I'd like to show you another example that uses our vacuum system over here. And there's a story that goes behind this. You know, there was a man that lived about 350 years ago named Otto von Guericke. He happened to be the mayor of a little town over in East Germany called Magdeburg. And you know, in addition to being a politician, he was also a scientist, something we don't have much today, scientists that are politicians. But he was, and he had invented a vacuum pump, one of the very early vacuum pumps. And he had an idea of taking two hemispheres. His hemispheres were about 18 inches in diameter, much bigger than these. And he simply put them together like this, and he took all of the air out of the inside, and then he put two teams of horses, one on either end, and tried to pull them apart. Well, we don't have two teams of horses, but I would like to take the air out and see what happens. So we'll put this on our vacuum pump. We'll close this valve. We'll turn the pump on. And you see the air is being removed because this is coming down towards zero. Now already you can see they're kind of stuck together. And as it comes down closer and closer to zero, eventually we get impatient, and rather than wait, we'll eventually just close this valve. Once that valve is closed, we can turn off the vacuum pump, let the air in as we did before, and then we can take the hose off, and we'll also take this little nozzle off, and we'll put right on here a handle. Now, as I said, we don't have 2 teams of horses, but sir, you look pretty strong. Can you help me pull this apart? No way. And that's because there's about 300 pounds of force pushing down on this. The pressure of the atmosphere is holding it together that hard. If we were to hang this from the ceiling and have someone pull on it that weighs about 300 pounds and try to do pull themselves up with it, they could perhaps pull it apart. Let's try it once more, and this time I'll let some air in. Not too hard, though. Okay. So you can do that with a pair of bathroom plungers at home, if you like. The same idea. If you have trouble getting them apart, just slide them a little bit like that and let the air in, and then they'll come apart. So that's an illustration of the pressure that the atmosphere exerts. Now, the reason the atmosphere exerts pressure is because the molecules that make up the air are moving around very rapidly. They're in motion. But you know, they're moving because the atmosphere has heat. And heat is a form of motion. And the hotter something is, the more rapid the molecules that make it up will move around. And so we're talking about the next area of physics, which is the physics of heat. And heat is a form of motion, the rapid motion of the molecules that make up the substance. Now, if we're going to talk about heat, we need to make some heat. For that, I'll take a match, and I'll turn on some natural gas into a little burner here and strike it to make a flame. Now, I want to do a demonstration for you that you can actually do at home if you're very careful. I have here a pop can. It's empty, and there's a little hole in the top where actually I drank it last night. And I have here a little bit of water. And so you could do this at home with a glass of water. You could pour a little bit of that water into a pop can, about like that. You may not have a burner like this, but you probably do have a stove. And you could put the can on top of the stove, like so. You have to be very careful, though, of course, because it's heat and you can easily burn yourself. While we're waiting for that, I want to do something else over here, and then we'll come back to it in a moment. Did any of you have one of those little pipes you put in your mouth and blow bubbles? You've probably seen them, though, right? We have a little pipe like that right here, except I'm not going to put it in my mouth. It's connected to a little tube that goes back to the same kind of natural gas that we're using over there. So I'm going to turn this on, let the natural gas flow in it for a moment, and then I'm going to put some soap bubble solution into it, just like you would get at a toy store or something. And we'll try to blow some bubbles, not using air, but using natural gas. And you see we're making some nice bubbles already. And one interesting thing about these bubbles is that they're lighter than air. So, consequently, they burn. And so if I take a match, I can ignite the bubble. So it goes right up to the ceiling. But it's flammable. So we can set it on fire. And in fact, this is kind of nice if we do it with the lights out. So I'll do it once more with the lights out. And you see a very nice flame from the bubble. And we can do this until we run out of bubble solution, which I guess we have now. So those are bubbles made out of natural gas. While we're talking about the physics of heat, and these are all examples of things that are hot, let me show you another example of something that's kind of the opposite of heat. It's something that's very cold. And I've got it in what amounts to a thermos bottle. And you can see something coming off the top, and that's not steam either. The stuff is so cold, it's condensing the water out of the air. Now I'm going to pour a little bit of this out and ask you if you've seen this before. What does it look like? Ice? What? Cool ice. Dry ice. You know, dry ice is a solid, and this is like a liquid. This is like water, isn't it? That's right, it's liquid nitrogen. Now you know nitrogen is, you're breathing nitrogen right now. Did you know that? Every time you take a breath, you're breathing in nitrogen. In fact, about 80% of the air you're breathing is nitrogen. But the nitrogen you're breathing doesn't look anything like this nitrogen, because the air you're breathing is nitrogen gas, and this is nitrogen liquid. Now, how do you make a gas into a liquid? You cool it down. Good answer. That's right, and that's what we did. In order to make this liquid nitrogen, we had to cool it down to a temperature of 321 degrees below zero Fahrenheit, or about 196 degrees below 0 Celsius. So it's really cold stuff, probably colder than anything you've ever experienced before. Now, there are many interesting things we can do with liquid nitrogen. And one thing I want to do is to take a small stainless steel cup, suspend it on a wire, and lower it down into the liquid nitrogen. Now, you see the nitrogen began boiling very vigorously. And that's a little strange, because the cup I lowered down into it wasn't particularly hot. It was at the temperature of everything in the room. But yet, compared to the liquid nitrogen, it was very, very hot indeed. And it was much hotter than is needed to boil the liquid nitrogen. Well, you notice after a little while, the boiling stops. And that happens because the cup is now cooled down to the very low temperature of the liquid. So if I take this out, I've got a cup, and what's in it? A little bit of liquid nitrogen. If I shake it, I can spill it, but I don't want to spill too much, because I want to take this little cup and lower it down into the steel cylinder, like so. And then I'm going to take a cork and hammer it on. And then I'll take the whole thing and shake it. And it went all the way to the back of the room, hit the camera operator up there, and ended up down in the audience about a third of the way down from the top. Let's see how our little can is doing. The thing is, I'm always too impatient, and I don't wait for it to come to a good boil. Now I think I waited too long, but let's try. There we go. And you see, we completely crushed the can. And that happens because there was steam in the can. When I turned the can upside down in the water, some of the water got sucked up into the can, and it cooled the steam down. And it cooled it down so much that it turned back into liquid water, and that left a vacuum in the can. And so just like the Magdeburg hemispheres over here, there was a very large force of the atmosphere pushing on the can. In fact, every square inch of the can had about 15 pounds of force acting on it. There's about 50 square inches, so there's about 700 pounds of force pushing on the outside of the can, and it just crunched it to almost nothing. So that's a very expensive way to crush your cans. Okay, well, these are examples of the physics of heat, and I want to now talk to you a little bit about another type of physics, and that is the physics of sound. Now, you may say, well, sound has nothing to do with motion or with heat, but sound is also a form of motion. When I'm talking and you're hearing, it's because my vocal cords are moving, they're vibrating, and that sets the air into motion. It vibrates, and the vibrations of the air move out to your ears where your eardrum vibrates, and then your brain interprets that, and you hear my speech. And so sound is a form of motion. And you may have noticed a little gadget over here. Do you know what this is? That's right, it's an oscilloscope. Looks a little like a television picture tube, and it's making a wavy kind of line in response to my speech. And the reason it's doing that is because this oscilloscope is connected to this microphone, and it's set up in such a way that it is illustrating what the sound wave would look like if you could actually see it. Of course, the sound wave is normally invisible, but here we make it visible by connecting it to an oscilloscope. And you can see the complicated pattern that results. But we can make sounds that are much simpler than the sound of my voice. And here's one way to do it. What is this? That's right. It's a tuning fork, a little U-shaped piece of metal. You hit it with a mallet, and it makes a sound. But I want you to notice what the sound looks like on the oscilloscope. And you see, it's a very regular kind of wave. And this is what we call a sine wave. A sine wave is the purest type of wave. It consists of a single frequency. Now I have here another tuning fork. Can you tell what's different about it? That's right, it's smaller. Would you expect it to make a higher pitch or a lower pitch? A higher pitch. Let's try it. And indeed it does. And I hope you see that there are more wiggles. The waves are closer together. The wavelength corresponding to that sound is shorter than the wavelength corresponding to the other sound. Yeah, good idea. Now I have a second tuning fork here that is almost the same as the first, except it has a couple of little weights up at the top here. And those cause it to have a slightly different sound. So I'll strike first this one, and then the second one. Can you hear a difference? It's ever so slight, a very tiny difference. Now what do you think? Somebody suggested that I strike them at the same time. Who said that? Good idea. Let's try it. Can you hear it go woo, 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 woo? Well, those are special kinds of sounds that we call beats. Beats occur when there are two notes that are very close together in frequency, but not quite the same. And you will get those kinds of beats. And in fact, musicians often tune their instruments by having one musician play a note, another musician plays the same note, and then if you hear beats, you know one instrument is slightly off tune. And so you adjust them until those beats go away, and then you know that they are playing exactly the same note. Now, speaking of musical instruments, these tuning forks make very pure waves, but a musical instrument makes less pure waves. It makes waves that are more complicated than the tuning forks. And every musical instrument makes its own distinct waveform. And we could try various musical instruments. I have one musical instrument here. What is it? Recorder? Does anyone play the recorder? Let's see. Who plays? Okay, come down. You used to play. What's your name? Turn around.
Julia?
Julia? Oh, that's a nice name. And I bet you learned this in school. Do they teach you this in music class?
Yeah.
They do, huh? So you learned this a few years ago, right?
Yeah.
And you haven't been practicing?
Sometimes.
Oh, you sometimes practice. Well, good. We don't expect you to play a tune, but maybe you could just play a few notes. Did you do that? Right close to the microphone, and let's look at what it looks like on the oscilloscope. Oh, very pretty. Thank you. And I hope you could see it was a more complicated kind of a wave than the tuning forks. And different musical instruments sound different. And in fact, in the back of the room, Renee Nesnadal on the synthesizer keyboard can simulate various instruments. Let's see what a clarinet looks like. How about some strings? You see, they're the same note, but they sound different, and they look different. Because they have what musicians call overtones, or physicists often call harmonics. And it is those overtones and harmonics, those additional frequencies, that make the musical instruments have their distinct sound. Now, I want to ask you another question. Do you think you need air for sound to travel through? You think so? No? Well, some people think yes, some people think no. In fact, of course, we are using air in order for you to hear me. But, you know, if I pound on this table with a hammer, sound travels right through the wood and the table. Now, you may say, well, you're hearing it because the sound comes out of the wood and through the air. But if you came down and put your ear on the table, you would all hear this very, very well indeed. Right? So sound travels through wood. It travels through marble. Here's a marble table. It travels through almost everything. But you know, there's one thing sound doesn't travel through. And I want to illustrate that with a little jar here. Can you see what's in the jar? That's right, a bell right inside the jar. Now I'm going to ring the bell, and it's not very loud because it's in a jar, but I hope you can hear it. Can you hear the bell? Okay. Now you may wonder why I ring a bell that's in a jar. That doesn't seem like it makes much sense, but I do this because I'm now going to remove the air from the jar, just like we did of these hemispheres over here. And we do that by putting the jar on this hose connected to the vacuum pump. Then we turn on the vacuum pump, and you can watch the needle there come down towards zero. And when that happens, we know that we are removing all of the air from the interior of the jar. Well, you know, of course, that you can never remove every last bit of air, so we'll wait until most of the air is out, as it pretty much is now. And then when we have most of the air out, we can now close this valve right here on the top. Well, once that's closed, we don't need the vacuum pump, so we turn that off. We can let air into the vacuum pump, and we can disconnect the hose. And now we have a jar with what in it? A bell. Anything else? A little bit of air. Good answer. Now what do you think will happen if we try to ring the bell? You won't hear it. You can hear just a little bit, can't you? And that's because some of the sound travels along this rubber hose and comes out. But if we could somehow suspend the bell in there without it being attached to that hose, you wouldn't hear it. So let's now let some air in, and I'll do it slowly and try to ring the bell while I do it. So there comes the sound back. So it is true that sound travels through almost everything except a perfect vacuum. And sound travels through gases, it travels through liquids, like water, and it travels through solids, like the wood. And when sound travels through something, if the speed of sound is different than what it is in ordinary air, it makes the pitch higher or lower. And I can illustrate that with an interesting demonstration, except I see here I forgot my balloons. Tom, could you get me some balloons? Sorry about that. Oh, my goodness, it's Krista Molman.
Hi, Professor Sprott.
Hi, Krista. Some of you may remember from last year, Krista and the Semitones sang the vocal version of The Wonders of Physics.
That's right. I see you're about to do one of my favorite demonstrations.
Oh, you do these demonstrations, I guess.
There's a group of graduate students here in the department that take a show very similar to this, not quite as big, around to area high schools, elementary schools. So if you see us walking around the halls in our red shirts, then you know we're going to do a show today.
Oh, that's great. You're a graduate student, and you study atomic physics, right?
That's right. I do atomic physics research.
Mm-hmm. You have 2 balloons. What are in your balloons?
I do. Well, there are 2 different gases here in the balloon. You see, this gas is lighter than air. The balloon's floating up. This is helium. And this gas is heavier than air. See, it stinks. This is sulfur hexafluoride. Now, you guys have been talking about that sounds differently as it travels through different media. Now, I think a lot of you are familiar with one of these demonstrations. If this is helium and it's lighter than air, what's it going to do if I breathe it? What's it going to do to my voice? It's going to go higher? You think my voice can't be any higher than it already is, right? Let's see what happens.
I know Krista is a soprano.
Hello and welcome to the Wonders of Physics. It's very good to have you here with us today. Now I sound a little bit like Mickey Mouse or maybe one of the chipmunks, huh?
So you see, my vocal cords, as they vibrate, the sound is traveling through helium rather than the air that I'm normally breathing. And so the sound actually travels faster, which makes the pitch go up. Now we mentioned helium's lighter than air, and that means that it flows out of my lungs on its own. So as I stand here talking, my voice is slowly coming back down to normal, and you don't think my voice is as high as you did before. So, now I do want to mention that this helium that I'm breathing is 99.9% pure. It's research-grade helium, and that means it doesn't have any oil or contaminants or anything that can make me sick by breathing it. A lot of times the balloons and things like that you'll get at the fair have things in them that can make you ill if it gets in your lungs and make you sick. So you want to be careful about doing these things. Now, if helium was lighter than air, and it made my voice go up, and sulfur hexafluoride's heavier than air, what's my voice going to do when I breathe this? Go down. Okay, let's see what happens.
Hello and welcome to the Wonders of Physics. So now you see I sound a lot more like Darth Vader instead of Mickey Mouse. This gas is heavier than air, and so the sound travels more slowly as I talk, and so I sound really funny. Now this gas is heavier than air, so I'm going to have to turn over to get it out of my lungs so I can breathe normally again. Excuse me just a minute. Okay, yeah, there we go. So,
well, that's pretty amazing, but you know, Krista, I notice you have another balloon way up over your head. What's in that?
Yeah, you're right. You know, I'm not really sure what's in it. A friend gave it to me.
Well, I wonder what could be in that balloon. Anyone have an idea? Hydrogen?
Helium? Wow.
Wow.
These people jump to conclusions, don't they?
Why do you think hydrogen? Helium? That's another good guess. Any other guesses? Hot air? Could be hot air. That's right. Those are all good guesses. How do you think we could tell whether it's hydrogen? Burn it?
Why not?
Why not, she says. Well, in order to do this, I'm going to take a stick, and put a match on the end of the stick, because I have to reach way up to that balloon. I'll strike the match. You notice Mr. Lovell with his fingers in his ears? Just in case it should make a noise, you might want to do the same. Well, that's amazing. Well, maybe Krista can stay with us for a little while, and maybe we'll find something for her to do a little later in the day. Well, these are examples of the physics of sound. And I'd like now to move on and talk to you a little bit about the physics of electricity. Now, electricity is everyone's favorite because there's so many interesting things we can do with it. Now, for the first electricity demonstration, I need someone to help me. Okay. All right. Come down here. Turn around. What's your name?
Colleen.
Aline?
Colleen.
Colleen. Okay, Colleen. You take science in school?
Yeah.
You do, huh? Is it a good subject for you? You like science?
No.
You don't like science? Do you like it any better having now that you're here today?
A little.
A little bit better, huh? Well, you know, that's why we do this, to make people like you like it more. And maybe eventually you'll like it so much that you'll be a scientist. Could that happen? Maybe? Well, you never know. It's worth working on you. Well, Colleen, we're going to have you demonstrate a Van de Graaff generator. Have you ever heard of that?
No.
Never heard of that. What I'd like you to do, Colleen, is to come right over here and step right up on this stool. Okay, I'll give you a hand. And we're going to take an aluminum dome like this, and we're going to put it right on top of this little plastic column. It has a belt, a rubber belt, that goes round and round. Colleen, can you put that hand right up there? You comfortable? Actually, let me move you out. Don't stay still. I'll just move you out a tiny little bit. Okay, you comfortable? Okay, now I'm going to turn this on, and whatever you do, don't move your hand. Okay? Leave your hand right there. It makes a little bit of noise. Don't let that scare you. Now, as we're beginning to charge this dome up, some of the electric charge is going off onto Colleen's body. And in particular, some of those electric charges are collecting on her hair. And electric charges repel one another if they're of a like sign, and consequently the charged hairs repel one another, and they try to get as far apart as they can. Now, shake your head. Colleen, don't you ever comb your hair? Now, the longer we wait, the more charge we'll get on her, but we can't take forever. And so I'm going to discharge the Van de Graaff generator, and I want you to watch your hair. So don't move your hand. Thank you, Colleen. Now, the reason we could do that safely is that she was standing on a plastic stool. Even though she was connected to something that produces 100,000 volts, there was no path for the electric current to go through her body. So it was perfectly safe for her to do that, so long as she was on an insulated stool of this sort. Now, I want to show you another demonstration that involves electricity, and I want to ask you where you've seen this before. So I'm going to turn it on and see if you've seen one of these. Where have you seen one of those? A light bulb? It's a little like a light bulb. Someone said a Frankenstein movie. In fact, you often see these in old science fiction movies, don't you? You know, you'll never see one of these in a modern science laboratory. But you do often see them in old science fiction movies. And they're gadgets called Jacob's Ladder. And it makes a wonderful prop in a science fiction movie, but it's really not very useful for much of anything in a science laboratory. But I wanted to show it to you because it does illustrate some principles of electricity. Those two rods are close together at the bottom, and we place about 60,000 volts between them, and that makes a spark. The spark rises up due to its own heat, and eventually it goes out because the rods get too far apart, and it restrikes at the bottom, and it does that over and over, much like the geyser. It goes over and over. Now, I want to show you another demonstration of electricity that requires a volunteer. Who will help? Okay. All right, come here. Turn around. What's your name?
Danny.
Danny?
Yep.
Okay, Danny. Hey, have you ever been out in a lightning storm?
Yep.
And there's lightning crashing all around and thunder and rain and hail? Doesn't scare you? No. Not in the least?
A little.
A little. Well, you know that's good, because you know if lightning were to ever strike you, that would be bad, wouldn't it?
Yeah.
Yeah. So you really don't want to be out around the lightning too much. You want to come inside when there's lightning, because you could injure yourself. We want to demonstrate something that has to do with lightning. You feeling brave today?
Yeah.
Oh, you are, huh? Well, that's good. Danny, what I'd like you to do is turn to your right and walk right over to this cage. And have a seat in what looks very much like an electric chair. Now, over on Danny's right is a 1,000,000-volt Tesla coil, and it produces lightning. And as long as you don't stick your fingers through the cage, you shouldn't feel a thing. You still feeling brave? Okay. Give Danny a hand. Well, that's pretty impressive, and we could do that safely because he was inside of what we call a Faraday cage. Now, the next thing we want to show you is much too dangerous to ask for any of you to volunteer. And so instead, we're asking one of our trusted assistants, Mr. Paul Nine, to give us a hand with this. Now, you notice we have over here a plastic stool that's a little bit taller than the plastic stool we had over here on the Van de Graaff generator. And that's because the Van de Graaff generator was only 100,000 volts. The Tesla coil over here is 1,000,000 volts. So we need a taller stool, but it's made out of a plastic, so it's a good electrical insulator. On top of the stool is a little tray, and in the tray is some water. And what we're going to do is put a metal plate inside that tray, and that metal plate is connected to the terminal of the 1,000,000-volt Tesla coil by a piece of copper tube. Now, you notice Paul has a crown on his head, and he has thimbles on his fingers. And he's stepping up onto this platform in his bare feet, stepping in this tray of water connected to the 1,000,000-volt Tesla coil. Now, don't try this at home. It's a very bad idea to work around electricity whenever there's water or whenever you're in bare feet. But we can safely do it here because it's being done under controlled conditions. Now, the crown on Paul's head is in the event that any sparks should come off his body. We want the sparks not to come directly off his skin, but off the metal on the crown. For the same reason, he has thimbles on his fingers so that his fingers aren't burned by the sparks that may come off his fingertips. You also notice that over here there's a fluorescent tube. Can you hold it up good and high? Just like the fluorescent tubes in the light fixtures above us. And I want you to watch that tube out of one eye, and out of the other eye, you can watch Paul Nine, the human voltmeter. Now, Paul is very brave to do that, but you notice now he has taken the thimbles off his fingers. And in order to protect his hand, we're going to give him, in his right hand, a discharge tube that's much like the fluorescent tube here, except it's clear so you can see the inside of it. And in the other hand is an ordinary, well, maybe not quite so ordinary, 2,000-watt light bulb. So once again, Paul Nine, the human voltmeter. Okay, and I hope you noticed that that fluorescent light that was out in the audience was lighting up. And in fact, there's electricity all around us all the time. And it doesn't do you any harm so far as we know. So I'd like now to talk a little bit about the next area of physics, which is the physics of magnetism. Now, a lot of people think that magnetism and electricity are different things, but in fact, they are closely related. And in fact, one way we make very large magnetic fields is with an electric current. And I have a demonstration of that back here. There's a device back here called a capacitor. It's like a large storage battery that stores electricity. And I'm going to charge the capacitor up, and then I'm going to discharge it into about 5 turns of copper tubing. And that's going to make a very large magnetic field. And before I do that, I want to lower another orange crush can down into the coil, like so. And then I'll push the button here after putting on my safety goggles, and we'll charge up the capacitor. Now you can tell it's charging because there's a meter here that's coming up to about 3,000 volts. And I'm going to charge it up to about 6,000 volts and then discharge it into this coil, and we'll see what happens. Now you notice Mr. Lovell with his fingers in his ears? If loud noises bother you, you may want to do the same. So we're about up to 6,000 volts now. Is everyone ready? Here we go. Look what it did to the can. It completely crushed the can. And that's because there was an electric current flowing around in the can, and that current were repelling one another, and it crushed the can. And I point out to you that the can is made out of aluminum, and aluminum is not a magnetic material. This is a magnet, and the aluminum is not at all attracted to the magnet, but it is attracted to the nails that I've got here. So that's a curious thing, a normally non-magnetic material that is rendered magnetic by putting it in a very rapidly time-changing magnetic field. Now I have another illustration of how that happens over here. So I'll take the magnet over, and here I have a coil with several hundred turns of wire, and it's connected to a meter that reads the electric current flowing in the coil. And if I just take this magnet and put it into the coil, you see the meter swings up. It swings up when I push it in, and it swings down when I pull it out. And so the time-varying magnetic field in this coil induces an electric current in the coil. And that's exactly the principle on which this can was crushed. Now, would you like to see me crush one more can? Okay, except this time I'm going to do something slightly different. I'm going to put a little plastic ring in here, and I'm going to take another can, this time a 7-Up can, and instead of putting it down in the coil, I'm going to perch it on top of the coil. Now the magnetic force is not squeezing the can, but it's pushing the can, like that. So, just to be safe, maybe we should, all right, put on my glove. And Krista, maybe you can lead us in a round of Take Me Out to the Ball Game.
You guys help me out here. Take me out to the ball game. Take me out to the crowd. Buy me some peanuts and Cracker Jacks. I don't care if I never get back, for it's root, root, root for the home team. If they don't win, it's a shame. For it's 1, 2, 3 strikes, you're out at the old ball game.
Okay, well, those are examples of very strong magnetic fields exerting forces on electrical conductors. I have one last example of that principle that makes use of a coil of wire over here that instead of connecting it to a capacitor, we actually plug it right into the wall. And so I'm going to plug that in, and then when I push this button here, that will energize this magnet, and that will induce an electric current in this little ring of aluminum. Again, it's aluminum, so it's not attracted to a magnet. But because there's an electric current induced in it, there will be a force on it, and it makes it jump up. That was pretty fast. Let's do it again. And it jumps off. Now, there's a way to make it jump a little bit higher. I have here a bar of iron, and if I put this on top of this iron that's down inside the coil, that will concentrate the magnetic field and extend it up higher. And now when I push the button, it goes up quite a bit higher. Once more. Now, there's a way we can actually make it go higher yet. And that has to do with the fact that the thing that is making it jump is the electric current that flows in this ring. And if I could do something to make more current flow in the ring, it would jump higher. Well, it turns out there's a way to do that. if we take this ring and cool it down to a very low temperature, it will be a better electrical conductor. Well, one way to do that is to put it in this little dish and to pour some liquid nitrogen over it. Now, this gives you a good opportunity to look at the liquid nitrogen. It looks like boiling water, doesn't it? And so, I'm going to take the ring. Now, I don't dare stick my fingers in there. I would instantly frostbite my fingers. So I'm going to use these special tongs to reach in and take out the ring, and I'll put it down on top of this electromagnet and energize it once again. So would you like to see that again? Do what? Okay, in the interest of science, we'll try it. Okay, so those are examples of what we call magnetic induction. Now I want to show you one last example of this principle, and that is this gadget over here, which has several hundred turns of wire that go around, and another coil down here with several hundred turns, and the currents go in opposite directions in those two coils. And that makes a magnetic field in the region in here. And I have here an aluminum ball. It's a little like a softball, except it's made out of aluminum. It's hollow and maybe about ½ an inch thick. And what I'm going to do is turn this magnet on, and then I'm going to lower this ball down into the magnet. Oop. And you see it is magnetically levitated. It moves around, but it stays there. And that's because the changing magnetic field, this is plugged into the wall, so it's changing 60 times a second, is inducing an electric current in the iron. And then there's a repulsion between the currents here and the currents in the iron that's suspended. Now we can also do that not with a ball like that, but with a cylinder like this. So if we put that in, oop, you see it kind of spins around, and it is magnetically levitated. Now I'd like to talk about the last subject of today, which is the physics of light. And I have an example of a gadget over here that will make light. And I want to roll it out and show it to you. This gadget is something that we call a laser. And the laser part is this blue thing right back here, and it produces a very intense beam of light. I'm going to turn it on, and you see right over Mr. Lovell's head, I'll put it right over to his right. You see that blue-green dot on the wall? If I shake it back and forth, you can see it a little better, I think. And that is the laser beam. And this laser beam is traveling through this tank. It's going in a window there and a window out here. And inside this tank is water, right up to about this level. And I'll tell you in a minute why we have water in the tank. But for the moment, I just want to call your attention to this laser beam. What I'm going to do is open a little trap door here and let the water actually flow out through this door. And that's why we have this trough down here, to try to catch the water. So I hope not to splatter people. Too bad. So I'll open this, and we'll let the water come out. And I want to turn the lights off, because this is really pretty neat to see. What you see is the laser beam traveling through the stream of water. And I can put my finger in it. It really almost doesn't even look like water, does it? Now, let's turn the lights back on for a moment, because I have to close the trap door, trying not to get wet. Not so easy. Okay. So there's the laser beam over Mr. Lovell's head again. Now, one last thing I want to do with this laser involves something you've all seen. Have you been out on a dark night and looked up at the stars? And have you noticed that sometimes the stars appear to twinkle? Have you ever wondered why they do that? Well, in fact, I can show you why they do that. Light travels through anything, including a vacuum. And one thing it travels through is the air. When the starlight reaches the Earth, it travels through the atmosphere. And you may not know that light doesn't travel in a perfectly straight line. In fact, if light goes through, you saw an example here of where the light was inside of a column of water, but also light traveling through the air is bent ever so slightly because of variations in the density of the air. And we can illustrate that by lighting this burner one more time. turning on the gas and making a flame. And we will see if we can make the star twinkle. And if I take it away, the twinkling stops. So this is exactly what happens when starlight reaches us from the Earth. It goes through the turbulent atmosphere, and it's made to twinkle in that way. Well, there's one last thing I want to show you. It's always tradition to conclude these presentations with one last demonstration in which I make for you a cloud. And in order to do that, I want to bring out a tank that has about 25 liters of liquid nitrogen, the same liquid nitrogen that we used earlier. And what we're going to do is force nitrogen gas into this tank. That will force the liquid up into this tube on the top, which has a bunch of holes on the top of it. The liquid will come out those holes, and it will be very cold. And it will cool the air above. And when you cool the air, the water vapor, the gaseous water in the air, will condense into very tiny droplets of liquid water. And that's what we call a cloud. And so I'll put on my hat, and I will thank you all for coming.